This is for Year 11 Methods. It's the class notes for inverse functions from the 11th of May, Part 2. Okay, inverse relations and functions. The inverse of is the reflection over the line y equals x. So I've got some coordinate points here on an axis, and I've got the reflecting line y equals x shown. If I reflect this point here over the line y equals x, I end up over here at 4, negative 1. This point here gets reflected to 2, 4. Notice that it gets reflected over the line y equals x. Negative 1, 0 becomes 0, negative 1. 2, negative 2 becomes negative 2, 2. 0, negative 4 becomes negative 4, 0. So we have a reflection over the line y equals x, and you can see that reflection. In actual fact, all we're doing is we're swapping the x coordinate and y coordinate over. The x coordinate was negative 1, the y coordinate becomes negative 1. The y coordinate was 4, the x coordinate becomes 4. So we're swapping the x and y coordinates over. Okay, what does that look like if I was to draw some functions that have been reflected over the line y equals x? So here's a function there, y equals 2x minus 4. Here would be the line of axis of symmetry, which is y equals x. This coordinate here, which is 0, 4, goes to 4, 0. This coordinate here, which is minus 2, 0, goes to 0, minus 2. So we end up with the reflecting line looking like that, which is a reflection about the line y equals x, that this curve gets reflected and becomes that curve. And we're swapping x and y values. What if I had the parabola that looked like that? Is it possible to do the inverse? We're reflecting over the line y equals x. What would the inverse look like? Well, the turning point, which was at minus 2, 0, goes to 0, minus 2. The point of the y-intercept at 0, 4 goes to 4, 0. And this point, which is minus 4, 4, goes to 4, minus 4. So we end up with a parabola looking like that, which you will notice is a reflection over the line y equals x. What would a cubic look like reflected over the line y equals x? That point there would go to 1, that point there would go to negative 1, that point there would go to negative 3. So I end up with and it ends up being reflection over the line y equals x. I would end up with an intersection point that would be on the line y equals x if it was extended. How do I find the equations of inverse functions? So I go back to my original question, which was y equals 2x plus 4. I drew 2x plus 4, then I drew the black line, which was the inverse. I was able to get them by swapping x and y coordinates. I do the same thing to find the equation. I swap x and y over, so x will equal 2y plus 4. Now to rearrange this for y equals, x minus 4 equals 2y, y will equal a half x minus 2. or the inverse function, is y equals a half x minus 2. Now you'll notice that the y-intercept for the black line is minus 2, and the gradient for the black line is a rise of 2 over a run of 4, or the gradient equals negative a half, which is what my gradient of my straight line is. What if I was trying to find the equation of a quadratic? So my original line is, or my original curve is y equals x minus 3 all squared, where x is greater than or equal to 1. I've drawn it here in red. I've also drawn the inverse in black. To work out the equation of the line, I swap my x and y's over. So x will equal y minus 1 squared. Just swapping x and y over. Take the square root of both sides. The square root of x equals y minus 1. Y equals the square root of x minus 1. Sorry, that's plus 1. No, that's plus 1 when I move it. Which is the equation of this square root that has been moved up 1. So we swap x and y over. One last little step is that of my original, which was y equals x minus 1 squared, x is greater than or equal to 1, the domain was 1 to infinity, and the range was 0 to infinity. And of my inverse, I got y equals the square root of x plus 1. The domain is 0 to infinity, and the range is 1 to infinity. And that because the domain is about x's, and the range is about y, and the domain is about x's, and the range is about y, that the range of the inverse is the domain of the original, because we swapped them, and the domain of the inverse is equal to the range of the original.